Welcome to the Deep Dive, your shortcut to being genuinely well-informed. Today we are wading into, well, a sea of digital noise, specifically around artificial intelligence. If you're listening, you definitely know the drill. Every single day, there's some new, often kind of impossible claim. AI is sentient, AI will cure cancer by lunchtime, AI is going to destroy all jobs by Friday. The hype is it's deafening.
It really is. And, it's a necessary correction we have to make here. A lot of the fantastic promise and, frankly, the resulting fears surrounding AI, it's just fundamentally unrealistic. It borders on what many critics, I think quite accurately, are now calling snake oil. So we've taken a deep dive into some really powerful sources, particularly looking at the framework laid out by thinkers like Narayan and Kapoor. Our mission today really is to arm you, the listener, with skepticism. It feels like a vital survival skill in this AI age.
That's such a critical distinction, isn't it? We're not just dismissing AI entirely. No, we're looking for a reliable compass, a way to navigate. We really need a framework to distinguish the genuine technological progress, the stuff that actually delivers, from the flashy, sometimes even harmful marketing claims.
Absolutely. And the difference, it often boils down to this. Is the tech tackling a specific constrained task, or is it trying to grapple with, open-ended real-world complexity in human context? We have got to separate the systems that truly deliver, like, say, advanced pattern recognition in medical scans from those that consistently fail or are just fundamentally flawed. Things like trying to predict future criminal behavior or deciphering genuine human emotion. If we can master that distinction, I think we can see through this fog.
Okay, let's unpack this framework then, starting with how the whole concept of intelligence itself might have become a bit of a distraction. I mean, for decades, the goal of AI seemed almost single-mindedly focused on mimicry, right? Getting a machine to act just like a person.
Yeah, that focus on human likability, it was really cemented by the Turing test. Originally, Alan Turing called it the imitation game. The benchmark was purely external. If an observer couldn't tell if they were talking to a computer or a human, well, the machine was deemed intelligent. It was purely a behavioral test, you see, not a test of what's going on inside, the actual understanding.
That makes sense historically, I guess, but why exactly does that focus on just the external mimicry? Why does that distract us today? What are the specific societal impacts we're missing because of that legacy?
Well, I'd argue it's done more harm than good, because it keeps us laser-focused on whether a chatbot sounds human, instead of asking what the technology actually does to society and whether that constitutes genuine intelligence anyway. I mean, look at biological intelligence, the neocortex. It doesn't operate by passing conversation tests, does it? Yeah. It's estimated to contain something like, 150,000 distinct sensory motor modeling systems, constantly creating updating reference frames for everything the body interacts with: sight, sound, movement, planning.
Right. So if our brain is made up of all these, 150,000 little prediction machines, all focused on sensory context, trying to mimic the result of all that complexity with current machine learning, it's kind of missing the point, isn't it?
Precisely. The underlying function of these cortical regions seems to be universal. There's Mountcastle's hypothesis, suggesting prediction is built right into the neuron itself. Dendrite spikes, priming activity thousands of times a second. It's incredible. But the output is entirely context-dependent. Connect those neurons to the eyes, you get vision. Connect them to the ears, hearing. Current AI, it tries to get this generalized intelligence by just scaling up data processing. It ignores the inherent parallelism, the redundancy, the context dependence of biological intelligence. And this distraction means we focus on the parlor trick, the chatbot sounding clever, not the societal architecture AI is actually building around us.
And that architecture being built, it's profoundly influenced by the profit motive. Which brings us straight to surveillance capitalism and this idea of extracting behavioral surplus. Can you break that down for us?
Sure. Surveillance capitalism, pioneered largely by companies like Google, fundamentally, it's an economic system where the main goal is extracting data. Data is the raw material. And the data they collect isn't just what you explicitly give them, like your search query. No, it's everything else. Your browsing history, your location, your psychographic profile derived from your clicks, even how long you pause on a video before scrolling on. That's the behavioral surplus. It's the data exhaust of your daily life that goes way beyond what's strictly needed to just make the service work better.
And how do they make that surplus useful? What's the end game?
They compile these enormous data sets into what are sometimes called unified profiles, or UPI data sets. Think of them as comprehensive, constantly updating data structures that integrate every tiny bit of information they can grab. And the whole purpose of creating these exhaustive profiles is to convert that data into incredibly accurate predictions of future behavior. Specifically, who's going to click on which ad or who's going to buy what product and exactly when they're most likely to do it.
Wow, it sounds like they're working to predict us so well that they can almost bypass our conscious choices.
Yeah, it really is the goal. And this whole process, fundamentally, it sidesteps user consent and, frankly, user knowledge. This, our sources argue, is a profound process of dispossession. It's not just about losing privacy, it's the systematic transfer of knowledge about you and therefore influence over you, from the many you, the consumer, to the very few who control these data structures. It's a dispossession of agency, really.
Dispossession, that's a really serious concept.
Uh-huh.
And what's almost tragic is that these algorithms, driven by pure profit, often seem to optimize for our worst tendencies, don't they? Not what actually brings us value or satisfaction.
Oh, absolutely. It's the engagement metric trap. Companies optimize for clicks, likes, comments. Why? Because those are easily quantifiable proxies for attention, simple numbers. But what makes us click? Often it's the inflammatory stuff, the sensational. The content we impulsively interact with isn't necessarily the stuff that makes our lives better or gives us genuine satisfaction. Not at all.
Can you give us a really concrete example of that, where the optimization caters to our sort of basest impulses?
Yeah, look at platforms like TikTok. Their algorithm has become incredibly good at optimizing for time spent lingering, just hovering. They track the duration you hover over a video before scrolling away, even if you never explicitly like it or comment or share. If you linger, the algorithm takes that as a sign of successful engagement. It learns this works. So this rewards what some have called digital rubbernecking. We often linger over sensational, high arousal, or controversial stuff, even if we know it's trashy. It triggers that low-level primitive impulse. The platform ends up catering to what's called the old brain, that desire for immediate arousal, rather than the new brain's reasoned desire for quality information or connection.
Right. So the architecture of surveillance capitalism, exploiting these engagement metrics, it drives us straight toward what you call the AI illusion, where this promise of automation masks the creation of a deeply, deeply divided society.
Exactly. The illusion is this mad rush to automate complex jobs and at the same time monitor humans much more intensely in the roles that remain. This push, it's leading us toward a truly two-tiered society. We see rapid income and wealth growth, but only for a tiny fraction. The computer scientists, the engineers, the financiers building and deploying these systems. Meanwhile, the majority of others, they struggle with job erosion, wage stagnation, or replacement by precarious, insecure ghost work. We'll probably talk more about that later.
And when we see this kind of technological reorganization leading to massive societal upheaval and inequality, we really have to look back, don't we, at historical precedents. This isn't the first time technology has kind of ripped open existing rifts.
Not at all. And recognizing these historical parallels is absolutely essential for understanding the political choices we face today. It's not inevitable. Think about the enclosures in Britain centuries ago. That was a technological and structural reorganization of farmland, moving from communal farming to private, supposedly more efficient plots. It was framed as progress, absolutely. But it pushed countless landless peasants into misery and basically created the urban working class under pretty dire conditions.
And a more recent, perhaps even more painful parallel.
Well, the cotton gin in 19th century America is just a profound example. A transformative piece of machinery, right? Exponentially increased the efficiency of processing cotton. Yet the reorganization of production around that technology didn't elevate the workers, did? No. Instead, it radically increased the demand for enslaved labor, cementing a horrific institution and pushing the already disempowered even further down into systemic oppression. It made things worse for many.
That really puts the current AI dynamic into stark relief. Technological reorganization, even when it's framed as inevitable progress, it's fundamentally a political and social choice. How we integrate AI today remains a matter of social and political choices. Are we choosing augmentation or replacement? It's not just some inevitable consequence of the tech itself.
And that is the core argument the listener really needs to hold on to. If it's left unchecked, technology consistently tends to push down those who are already struggling. History shows us that.
Okay, now let's apply our framework more directly. Constrained tasks versus complexity. We have to acknowledge where AI has shown genuine, powerful capability, mostly in tasks based on high-volume data processing and specific pattern recognition. Where is that success really undeniable?
The most immediate and, frankly, powerful success story is in computer vision, without a doubt. The breakthrough moment that really catalyzed this current wave of deep learning was back in 2012. AlexNet, a convolutional neural network. It achieved this unprecedented leap in image recognition performance, roughly 10% better than the previous state-of-the-art. That might not sound like much, 10%, but it was the pivot point. It demonstrated the massive, real-world viability of deep learning for vision.
And the result is, I mean, computer vision is now absolutely everywhere, isn't it? It's not some academic novelty anymore.
Correct. It powers factory robots doing highly specific quality control checks. It's in airport scanners, flagging anomalies instantly. We use it every single day in our smartphones for facial authentication, sorting photos. And critically, it underpins the whole shift towards autonomous or semi-autonomous driving systems, helping cars interpret a defined visual environment. It has clearly exceeded human capacity in these highly constrained, high-speed visual pattern tasks. No question.
And maybe the most life-altering application of this pattern recognition ability seems to be happening in medicine. We're seeing machines actually outperform human experts in specific high-volume tasks.
Yes, this is where that constrained framework is just perfectly illustrated. The FDA has approved deep learning systems for medical images. Companies like Arteries, Wiz.ai, are doing this. Now, the machine isn't asked to diagnose a person's overall health or decide on treatment. No, it's asked to do one thing: find a specific pattern reliably and very, very quickly.
Can you elaborate maybe on the scale and accuracy? How much better is it? That feels like the key nugget here.
Okay, take the work of Zebra Medical Vision as a great example. They deployed a system, a convolutional neural network, specifically designed to detect vertebral compression fractures in X-rays and scans. Now, the human element here is crucial. Human radiologists, they're under pressure, high volume. They often miss these kinds of fractures more than 10% of the time. Zebra Medical Vision system. It achieved 93% accuracy.
Wow, a 7% improvement on a critical diagnostic task like that
Yeah.
it's immense. But what about the speed and the cost?
That's the other part of the revolution, really. These systems can process millions of scans at a speed that's, well, it's estimated at nearly 10,000 times faster than a human radiologist.
Yeah.
And the cost, as low as maybe $1 per scan. Now, this isn't replacing the doctor, right? It's augmenting the system. It dramatically reduces errors in those high-volume repetitive tasks. It fits the definition of true, valuable AI progress perfectly. High accuracy in a highly constrained environment.
And it's not just image recognition, is it? Our sources suggest a similar kind of displacement happening in more role-based language tasks.
Yes, absolutely. For many language tasks that are, let's say, transactional, high volume, and don't require deep cultural understanding or semantic nuance, AI is rapidly displacing human workers. Our sources suggest that most translation work, for instance, is likely to be largely displaced by AI in the coming years. And again, this is a success built on pattern matching sequences of words in one language to the most probable sequences in another. It's not built on the kind of deep semantic understanding that really characterizes a human mind.
Okay, but the moment we shift, the moment we move away from that constrained, high-volume environment into the real world, which is highly complex, uncertain, the framework predicts failure, right? And the classic example of this persistent failure is the holy grail problem of autonomous vehicles. AVs.
AVs definitely remain the holy grail precisely because driving is so messy. I mean, initial predictions were wildly optimistic, remember? Self-driving cars by 2020. But now sources are suggesting full AV technology. We're talking level 5 autonomy probably won't reach maturity until 2041, maybe even later. The failure is really due to what we call combinatorial complexity. Driving involves thousands of tiny subtasks, and the environment is constantly throwing up unforeseen variables. Unpredictable weather, a pedestrian stepping out, an oddly shaped box falling off a truck.
Yeah.
Things that training data might never have seen in exactly that way.
Yeah, I've heard people compare the challenge of AVs to mastering a game like Go, which famously has more possible positions than atoms in the universe. But even that massive complexity, it doesn't really compare to the real world, does it?
No, not even close. Because in Go, the rules are fixed, the boundaries are known, the environment is absolutely certain, even if complex. The real world, it has no fixed boundaries, no fixed rules, really. The complexity isn't just about the number of variables, it's the infinite potential combinations of those variables. As one Air Force report pointed out, even in a simulation, a simple physical problem, like anticipating when an overflowing cistern might cause some secondary effect downstream, even that can be hard to foresee and model accurately. So fully testing every possible real-world scenario that a complex autonomous vehicle might encounter is, well, by definition, Effectively impossible.
That's the crucial failure point, isn't it? Impossible to test everything. Okay, beyond self-driving, let's critically evaluate two other areas that seem to rely heavily on potentially flawed assumptions about the world:
Hmm.
predictive policing and emotion recognition.
Right. These are prime examples of the dangers of deploying AI, where context and complexity matter most, and where the data itself is often deeply problematic. Predictive policing systems, they're designed to forecast where and when crime might occur, but they are almost always trained on deeply biased historical data sets, data that reflects historical patterns of over-policing in certain communities, often minority communities, so the output just reinforces the input bias, becomes a feedback loop.
And our sources really highlight how ethically compromised the raw data used for training these systems often is.
Absolutely. I mean, consider the use of mugshot data sets, like something called the multiple encounter data set. These images are used purely, and the sources are explicit here, to refine tools, techniques, and procedures for face recognition. The people depicted. They have no say in how their images are used. There's no consent whatsoever. Furthermore, these images often show subjects who have clearly just endured violence, and you see scars, bruises, their ethical standing, their basic humanity. It's completely ignored. They are simply data points, features to refine tools for that surveillance architecture we talked about earlier. This is dispossession in practice. It's raw.
Treating people as mere features for an algorithm, not individuals with rights. Okay, then we move to effect recognition, or what's more commonly called emotion recognition.
Effect recognition, yeah. It's been heavily commercialized. The companies like IBM have jumped into this space. Yet, these systems consistently fail because they struggle profoundly with human context and nuance. Emotions just aren't simple, singular signals that you can reliably read purely from a facial microexpression or someone's doing a voice. It's much more complicated.
Why is that complexity so fatal to these systems? What's the core issue?
Because human emotional expression is highly dependent on embodied states, subjective feelings, and dynamic context. A scowl might mean confusion, deep anger, or just intense focus, depending entirely on the situation. We don't express emotions as these universal, discrete, objective signals that a camera can just read like a barcode. The machine sees a pattern, say a downturned mouth, and it assigns a label sadness without any access to the semantic context. Maybe they're just trying to solve a really hard math problem. This failure is intrinsic, really, because the task itself is ill-defined and inherently non-constrained. It's trying to measure the unmeasurable in a simplistic way.
Okay, so moving from these practical failures to more philosophical, theoretical limits, we really have to confront the most immediate problem facing large language models right now: the hallucination problem. Anyone who's used ChatGPT or similar tools knows they just make things up sometimes. Let's talk about the mechanics. Why did they do that? Why hallucinate?
Well, the primary reason is that LLMs don't know anything in the human sense. They lack semantic meaning. They don't understand concepts. They function by storing incredibly vast statistical patterns about which tokens, which are words or pieces of words, are likely to follow other tokens based on the massive amount of text they were trained on. So when you pose a question, the model generates an answer by picking the next most probable token, then the next, then the next. It is fundamentally making up the answer on the fly, purely based on probabilities learned from text.
So it's not really an engine for knowledge retrieval. It's more like an engine for ultra-sophisticated probabilistic autocompletion.
That's a great way to put it, exactly. Imagine a predictive text system that has swallowed the entire internet. It can sound incredibly confident, very authoritative, even when it's completely inventing sources or dates or scientific concepts. But here's what's really fascinating: this tendency to hallucinate. It's often deliberately engineered to some extent into the model.
Wait, you're saying they want it to hallucinate at least a little bit? Well,
Well, they need randomness. If a model sticks too closely to the exact patterns in its training data, which is technically the safest, most factual path design, it becomes what's called overfitted. Overfitted models tend to generate highly similar, very uninspired, sometimes just repetitive or irrelevant results. They get boring. So to avoid being boring and to encourage a bit of generalization and maybe even creativity, model designers intentionally add a degree of randomness, sometimes called temperature or noise, into that process of picking the next token. But that necessary addition of randomness, the thing designed to foster originality, well, it correspondingly raises the likelihood of factual hallucination. Making stuff up. It's an inherent fundamental trade-off in these current architectures: originality versus factual certainty. You can't perfectly maximize both at the same time.
that inherent limitation, the total reliance on pattern and probability and not meaning, leads us right to that foundational philosophical limit, the one separating LLMs from human minds. The problem with syntax versus semantics. Does just manipulating symbols actually equate to real understanding?
This is really the crux of the debate, isn't it? And it's captured perfectly by John Searle's Chinese room thought experiment. The argument asks us to imagine a person, let's say an English speaker, walked inside a room. They don't speak a word of Chinese. Slips of paper with complex Chinese characters are slid under the door. These are questions written in Chinese. Now, next to the person is a giant rule book written entirely in English. This rule book tells them exactly how to manipulate those Chinese symbols based purely on their shape and their arrangement, their formal rules, their syntax.
So they're just a perfect symbol shuffler, following the rules precisely, but without any idea what the symbols mean.
Correct. Following the syntax perfectly, they push back new slips of paper with different Chinese symbols, the answers. Now, from the outside, the person asking the questions would receive perfect, coherent answers in Chinese, indistinguishable, perhaps, from answers given by a native Chinese speaker.
So the machine, or rather the man in the room, has passed the behavioral test, the Turing test with flying colors, looks intelligent from the outside.
Absolutely, past the imitation game. But, and this is the critical point, the person inside the room does not understand one single word of Chinese. Not one. They only have the rules for manipulating symbols. They completely lack the semantics, the content, the meaning, the actual understanding. Human minds are both semantical and syntactical. We understand meaning and structure. Current computer programs, including LLMs, are purely syntactical. They manipulate symbols without any inherent meaning. Their output only seems to be about something because we, the human interpreters, assign meaning to those strings of tokens they produce. That deficiency, that lack of semantics, is a profound intrinsic limit to current AI systems ever becoming a true mind.
That makes perfect sense. Syntax isn't semantics. Okay, so if true intelligence involves more than just formal symbol manipulation, where does that leave the current success of deep learning, which has, after all, moved away from that old symbolic AI towards these powerful neural networks?
Right, the current deep learning successes definitely came from abandoning those older, brittle, symbolic AI approaches. Those relied too heavily on pre-programmed explicit rules and representations. They couldn't handle ambiguity well. Neural networks, by contrast, they allow data to be filtered and patterns to be recognized without needing explicit rules written down beforehand. That yields these powerful outputs we see. However, when we compare this success to the ultimate biological reality of the brain, we bump into another set of limits, computational limits.
Okay, let's delve deeper into that biological contrast then, especially regarding computational capacity. How does the brain differ?
Well, biologically, the brain exhibits incredible parallelism and redundancy. It's doing many things at once, and it can cope with damage. Unlike a computer program that might crash if one critical component fails, people can often make a remarkable functional recovery after something like a stroke. Why? Because other parts of the brain can often take over the lost function. There's backup. Furthermore, the neocortex, operating based on principles like Mountcastle's hypothesis, demonstrates this universal function prediction. But that function is distributed across maybe 150,000 different systems, all running in parallel, all interacting. It's an architecture built for incredibly complex, multi-layered processing, not just generalized token prediction based on statistical patterns.
So how does that biological architecture challenge the current deep learning paradigm? Where's the computational limit?
It leads to what some researchers call the ultimate computational trade-off. The more you want a computational system to make true use of sophisticated computational capabilities, things like internally recomputing on data, handling complex feedback loops, exhibiting the kind of parallelism and redundancy we see in the brain, the more that system is going to exhibit something called computational irreducibility.
Computational irreducibility. Okay, that sounds like a pretty complex term. How should we understand that conversationally? What does it mean?
Think of it this way. A system is computationally irreducible if the only way to find out what it will ultimately do is to actually run it and watch it step by step. You can't create a simpler, faster shortcut to predict the final result accurately. You have to perform the full computation. The biological brain, with all its interacting parts, is likely highly irreducible. But here's a limit for current AI. The more a system shows this computational irreducibility, the less trainable it becomes through the standard, efficient neural network optimization techniques we rely on, like backpropagation.
Ah, okay. So to make the neural network trainable and scalable to get that breakthrough speed and accuracy we see in computer vision or language models, we have to inherently limit its capacity for the kind of deep, internal, complex computation that the biological mind seems to rely on.
Precisely. It's a fundamental trade-off. Current, highly trainable neural networks are inherently limited in the depth and complexity of computation they can perform internally. Why? Because they must prioritize efficiency, scalability, and statistical prediction over that slower, messier, context-aware, irreducible reasoning. This is why AI excels at pattern recognition in constrained domains, but hits a wall when dealing with the true, messy, unpredictable irreducibility of the real world and genuine understanding.
Okay, the theoretical limits are one thing, but the immediate systemic dangers of just uncritically deploying AI, they're massive, aren't they?
Yeah.
Impacting millions globally right now. Let's start with the concept that makes AI appear so magical and instant: ghost work. What exactly is it, and how big is this hidden human cost?
Ghost work. It's the staggering amount of invisible human labor that's required to build, label, clean, and refine the massive data sets that actually fuel AI systems.
Right.
We just don't see it. It's estimated that roughly 20 million individuals globally are involved in this kind of work. They are the hidden backbone of AI. They're often performing incredibly repetitive, tedious tasks like drawing boxes around objects and images to train computer vision models, or transcribing snippets of audio to refine language systems, or checking if AI outputs are offensive.
20 million people. That's like the workforce of a small country, operating entirely in the shadows, and they're often working without any traditional employment protections, right?
Overwhelmingly, yes. They are classified as independent contractors, not full employees. The employment model strongly resembles 19th century piecework. Workers get paid tiny amounts for each small task completed assembling digital components for pennies, essentially. And this model is often deliberately engineered to exploit legal gaps. Specifically, it takes advantage of the definitions established by historical labor legislation, like the Taft-Hartley Act in the U.S., which set up strict tests for classifying someone as a full-time employee versus an independent contractor.
So companies are basically using this contractor loophole to scale their AI development incredibly rapidly while completely bypassing any long-term investment in employees, benefits, job security, or basic labor rights.
Absolutely. The perceived magic of AI is largely built upon this foundation of precarious, unprotected, invisible labor. The ghost worker bears all the risk: no healthcare, no guaranteed hours, no retirement plan, no long-term security. Meanwhile, the company reaps the massive benefits: the behavioral surplus, the predictive power, the efficient model training. This feeds directly back into that two-tiered society we discussed earlier. The few gain agency and incredible wealth, while the many are dispossessed not just of data, but also of secure, dignified labor.
Okay, let's switch gears to another systemic danger, one where the stakes are, frankly, infinitely higher: autonomous weapons in military applications.
Yeah, this area really showcases the same constrained versus complexity dichotomy, but with potentially fatal consequences. Our sources suggest that developing, say, autonomous anti-tank engagements is considered far more feasible than systems designed to reliably discriminate human targets on a complex battlefield. And the reason is pretty simple. Tanks are, quote, distinctive military vehicles. Recognizing them fits the definition of a relatively constrained pattern recognition task. The system needs to look for metal, certain shapes, specific thermal signatures, things that are somewhat predictable patterns.
But even with relatively constrained targets like tanks, when you introduce the sheer complexity and chaos of a real battlefield, the risk must skyrocket, right?
Yes, absolutely. Because the fundamental safety risk here is that fully testing all possible scenarios a complex autonomous system might encounter in the field is, by its very nature, impossible. The number of potential interactions, unexpected variables, environmental conditions, electronic warfare, system-to-system failures, you simply cannot exhaustively model or test all of that before deployment. This is that real-world computational irreducibility coming back to haunt us, but with weapons.
And what about the safeguards? The measures designed to prevent runaway systems, the human circuit breakers or kill switches we hear about, are they a reliable failsafe?
They are definitely vulnerable. Look, if that circuit breaker relies on software, and almost all modern complex systems do, then it's susceptible to the exact same risk as any other piece of software. Hidden bugs, vulnerabilities to hacking, or simple communication failure at the critical moment. It's not like a big physical red button anymore. It's another layer of potentially flawed code. The inherent vulnerability of complex software systems means a simple kill switch is absolutely not a guarantee of control when things go wrong fast.
We often hear about the fear of a flash war, where autonomous systems trigger global conflict in milliseconds. Based on the sources, is that a realistic danger?
Well, a conflict escalating in mere microseconds is probably unlikely. Missiles and robots still take physical time to move. Decisions propagate through networks. However, the danger is still immense. Runaway autonomous weapons could absolutely cause a significant number of deaths and rapidly escalate crises over a matter of minutes or hours. They could push nations past the point of no return before human political judgment or diplomacy can even catch up or intervene effectively. The speed of escalation is the critical danger.
So if the technology itself is often intrinsically limited in its scope and it's inherently dangerous when deployed uncritically, whether that's in warfare or in the workplace, displacing people, what are the paths forward? How do we manage this powerful wave?
The path forward really requires political will, not just waiting for some magical technological refinement that solves all the problems. Our resources identify two major avenues for change, broadly speaking. The first is clear, strong regulation. We need to set ground rules for companies on how they build and how they advertise their products. We need to prevent the peddling of AI snake oil. This means imposing real accountability for the claims made about AI capabilities, especially in high-stakes areas like employment, healthcare, and justice.
Okay, regulation is one path, and the second focuses more on how we structurally integrate AI into society itself.
Exactly. We have to consciously choose how we integrate AI, framing it as a matter of social and political choices, rather than inevitable consequences of the technology itself. That framing is key. The critical decision point again and again is whether we use AI primarily to augment human jobs, making them safer, easier, more productive, maybe even more creative, thereby empowering workers, or whether we use AI strictly for replacement, which simply widens the societal rift, concentrates wealth further, and disempowers large segments of the population. That choice augmentation versus replacement is the fundamental social and political decision we face right now.
Okay, so we've really established a clear framework today, I think. AI is not magic, it's a tool, and it fundamentally excels at pattern recognition, but only within constrained, high-volume data sets. Think about the accuracy and speed we discussed in medical image processing or basic transactional language translation. It delivers immense proven value in those narrow scopes.
But, and it's a huge but, it struggles intrinsically and profoundly with semantic understanding, with real-world complexity and ambiguity, and with avoiding the biases that are baked right into its creation. Biases stemming from the exploited labor of ghost workers, from the dispossession inherent in the surveillance data model it feeds on. The danger isn't just about privacy loss or corporate monopolies, though those are serious. It's about the systematic structural transfer of knowledge, power, and rights from the many to the few, often conducted in what one source beautifully called a glorious fog of automagic. Clear-minded scrutiny, that skepticism we talked about, is really the only antidote.
And that fog of automagic, it brings us right back to that internal human conflict, doesn't it? The battle between the, let's call it the old brain and the neocortex. Our primitive brain, that old brain, it loves simple narratives, right? It likes the immediate satisfaction of just eating the cake. And it's easily swayed by the appearance of inevitable power, of magic. The neocortex, though, the newer, more reasoned part of our brain. That's the part that understands mechanics, complexity, nuance, delayed gratification. It can hold its breath, so to speak. So here is the final provocative thought for you, the listener, to carry forward from this deep dive. If the temptation to believe in magic is an inherent human impulse, how much of the current AI hype, all those breathless promises of inevitable world-changing superintelligence arriving any day now, how much of that are we consuming simply because it caters to the old brain impulse? The impulse to believe in magic and inevitability, rather than engaging the reasoned analysis of the new brain, the part that understands the mechanical limits, the hidden ghost work, the mathematical constraints of a purely syntactical machine. Think about that framework we discussed, constrained success versus real-world complexity and failure, the next time an AI promises you a shortcut to the moon.